We got Brian Johnson from Tavus, who's going to be talking about real-time conversational AI. When I first saw this thing, I was like, this is cool. This is like super cool. You're going to love it. All right, Brian, come on up.
Hello, everybody. Well, I'm Brian. I am a father, a husband, and an engineer. I work at Tavus. I'm a staff engineer. I'm here today to talk to you all about conversational video interface, which is something that we just launched last week. I'm one of the engineers that worked on it. And I want to thank you all, first of all, for coming here to this talk. I'm sure you have a lot of different reasons for coming here. I'd love to know if anybody came here to hear about this, so hit me up afterwards if that's the case for you. So this talk is about one of my primary focuses in this project, which is the utterance-to-utterance speed. So that is the amount of time it takes from when you stop talking to when someone else in a conversation starts talking, all right? And then what were the challenges around achieving a lifelike, human-like utterance-to-utterance, and how did we do it? So that gets to the question of why is real-time conversational hard? And maybe you're wondering, what is real-time conversational? I'll get to that. But just imagine when you're talking to someone, that's a conversation. So if I'm talking to you and I say, hey, how's it going? If you wait that long, it's kind of awkward. But you know, in a conversation where we're really vibing, you're going to respond like right away. And so what we aim to do was to, well, let me just say, like, I'll pass over this, was that we aim to create an API that lets you create a conversational replica of yourself that you can put out there, and it can have conversations with people on your behalf. All right? And so the goal here was to have a lifelike replica or a lifelike conversation. So that means it has to respond fairly quickly. The model we use under the hood is a proprietary in-house model that we've had for, well, really only since like March. So it's pretty new itself as well. But it's completely built in-house. It's all proprietary. We have a machine learning team that is doing research and built this model. And we also just recently shipped a second version of that we call Phoenix 2, which is more advanced. So this model generates a video from audio. So it takes in a voice audio and generates a video. And then with that model, we've created the conversational video interface, which allows you to take that replica of yourself and put it into a web page, embed it in a web page, and allow that replica of you to have conversations, or let's just say, since we're all developers here, you can use this technology to allow your customers to put their presence out there, their replica, to have conversations with their customers. If that made any sense. Maybe not. It will soon, I hope. And I'll have some time for questions here pretty soon. Let's see. So the conversational video interface looks something like this. So let's say you are an online learning company and you want to put teachers out there. So you have a teacher in-house, and let's just imagine this woman in the larger picture is a teacher. She can authorize her likeness to be used on with our technology, and then put out a interface on the web where people can join, like a Zoom meeting, with her replica, have a conversation, learn about the things she knows about, and it feels kind of realistic. Now you're going to know it's a replica, but it feels good. It feels natural. And so what we've worked on is developing the world's fastest conversational interface, which has a less than 1 second utterance latency. That's the time between the two turns of the conversation. It's the most realistic in terms of the naturalness of the conversation, but also the visual quality and the audio quality of the replica. So it really feels real. It's also plug and play. So we allow you to bring your own LLMs, your own TTS, pretty much replace any part of the pipeline with something you want. But then we also offer highly optimized versions of all of these things that you can use right out of the box. So the reason I'm having this talk is because of some research that I read about, that conversations that can be observed by a third party that look like the two people are vibing, that look like the two people are having a good conversation, tend to have an inter-utterance delay between the two turns of speaking of around 250 milliseconds. Now think about that. It's really fast. It's like somebody just, okay, so I'll mock it. So it's like, hey, how are you doing? Oh, I'm doing good. That's about 250 milliseconds. It's really, really fast. And when I first started working on this, that didn't make any sense to me. But as I've been thinking about this more and more over the past couple of months, I started to realize that is how we have conversations. Not only that, but we often actually interrupt each other. And so the research shows that the modal response time between two turns is anywhere between negative 1,000 milliseconds and around 1,500 to 2,000 milliseconds. So a lot of times in really good conversations, we're actually interrupting each other. We're starting to talk before the other person isn't done. That sounds kind of like wrong, but it's been shown to be true, not only in a single culture, but in all cultures. It's amazing. It's in all languages and all cultures. It's kind of a universal thing for humans. But the modal response time, the one here in the middle, is 200 milliseconds. And that's been shown to be what you can observe to see whether two people are sort of having a good time in their conversation. And so we didn't want to aim for that because it's pretty hard to hit, and I'll talk about why. But what we decided to do was let's go get below a second, because as you can see here, below a second is kind of starting to show up on the curve. So not only that, but for humans, thinking is part of the conversation too. We can't just blurt out something random. So if somebody says, hey, I'm having a bad day, and you say, great, that's not a good conversation. You got to actually have some time to think about it. And for humans, that time to come up with a thought is from after hearing someone is about 700 to 900 milliseconds. And there's kind of a disconnect here in my head. I'm like, okay, if we have to respond within 200 milliseconds, and it takes us 700 to 900 milliseconds to think of what to say, how do we do that? Anybody have an idea? Oh, you think ahead. You got to think ahead. So, but what if somebody's not done talking yet? Then what if the last thing they say is the most important? These are the kinds of questions that you have to deal with when you're thinking about a conversational video interface like this. But the good thing is that LLMs are pretty fast at thinking, and so that comes into play here as well. But we want to keep in mind that 200 milliseconds is actually the time when people are vibing. So if you're having a really good conversation, 200 milliseconds is what the inter-utterance delay should be. But if you're starting to get to know each other, if you're asking like a deep question that someone needs to think about, it might take 700, 800, 900 milliseconds for them to respond, because they actually have to think about what you're saying. So let me go step back a little bit and talk about what we needed to build. So what we wanted to build was something that when you sat in front of the camera, it looked like a human being. It looked like a person. It looked real. It sounds like a person. It sounds real. It can see you. It can hear you. It can have a conversation with you that's logical, based on the history of the conversation, and that it would respond proportionally to the way you're talking to it. So if you said something short, it's not going to go on a long rant. It's going to say, if you said, hey, how are you doing? It goes, yeah, I'm doing pretty well. Instead of, yeah, I'm doing pretty well. I had all these problems yesterday, but today was pretty good. You don't want to, that's not a great conversation maybe. But we wanted to make it so it was proportional. It should also be interactive. That means that when you start talking, it needs to stop and start listening, even if it's already talking or mid-thought. Okay, so meet Carter, which is kind of like our internal name, which stands for Conversational Real-Time Replica. We've changed the name since then to Conversational Video Interface, but we kind of affectionately call this Carter. And Carter is a conversational replica. And I'm going to show you here.
What can I do for you?
I guess my audio is not hooked up, is it?
Experience. What do people tend to ask you?
Thanks for joining me.
Can you hear that at all?
Enjoying the experience.
No.
Most people ask me about new feature
Okay.
updates or
Let me see if I can get audio going here real quick. Decimator? No. Decimator. I don't know. I'm going to try it.
want to know more about our AI technology. Some even just want to chat about their day and share a funny joke. How about you? What are you curious about?
I like jokes. Can you tell me a funny joke?
Here's one. Why couldn't the bicycle stand up by itself? Because it was too tired. Haha. How was that? Did I make you chuckle?
It definitely made me chuckle. A lot of LLMs know that joke. I wonder why.
I guess that joke didn't impress you with its originality. Well, I won't take offense. I'm sure there are plenty of people out there who know a million too tired bike jokes. If you want another one. Or maybe something else. What do you say?
Oh, I definitely wasn't criticizing. I think you're very impressive. I'm curious what you can see also, as well as what you can talk about.
Al, thanks for the kind words. I'm glad to hear that. As for what I can see, well, I'm seeing a friendly person with a great smile and a background that looks like a cozy office or study. A warm and quiet space to get things done, or maybe just to relax. Is that about right?
That's definitely about right. I like warm, cozy spaces. Your space looks great. Who designed your space?
Thank you, I'm glad you like it. As for who designed my space, well, to be honest, I don't actually have a space of my own. I'm just a digital presence, so I don't need a physical office. But I'm happy to chat with you here and make you feel like you're in a cozy space.
Do you live in a simulation? Sometimes I think we all live in a simulation.
The simulation idea, isn't that a fascinating topic? I'm with you, it's definitely a possibility. I mean, who's to say what's reality, what's not? It's mind-bending to think about.
It definitely is.
The digital world.
Thanks for talking to me today.
We've reached the
Okay.
end of our conversation for now.
So that is, where did I go? Let's see, here we go. Yeah, so that's just a demo of how it works. You can go to our website right now, tavus.io, and try it out for yourself for free. It's there for anyone to try. We basically put it up on Product Hunt and got #1 product of the day, so thanks. Now, you've probably all seen audio to audio, right? Like the ChatGPT, like some of these other ones that are audio to audio. And the key distinction between what we're doing and what something like that is doing is that video is 10,000 times the size of audio. There's a lot more data to pass around. It's tricky in terms of bandwidth, and it's tricky in terms of latency to get everything to work that well. Fortunately, we had a lot of good partners. One of those partners was Daily, that helped us, Daily.co, that helped us with streaming. But we also had to apply some tricks and tips of our own just to get that data passed around on the inside of our conversational replica as well. And I'm going to talk about some of the tools we used to make that happen. So our goal was less than 1 second of utterance to utterance. And these are the 5 tools that we applied. These are kind of generic, and I didn't want to get into too much detail because these things change in terms of the implementation. And a lot of these should be pretty obvious to you, I hope. Things like streaming. So streaming is the concept of sending smaller bytes instead of sending larger chunks, and that allows you to get a faster time to first byte. Okay? Parallelism. Parallelism allows you to do multiple things at the same time. Using your resources as much as possible. So on any computer, you have a certain amount of resources available: CPU, GPU, RAM, disk, network, and you've got to be aware of all those things and know what you have available and know what you can use to your advantage. Memory. Memory is much faster than disk. And the closer the memory is to where you're using it for computation, the better, the faster. But oftentimes, the closer you get, the less of it there is. And then memory sharing. The more you can kind of share memory, the less you have to move things around. So let's talk about streaming for a second. It'll be way faster if we do streaming. This is kind of a recurring concept for us when we were building this. It was like, well, how do we get faster? We should do streaming. It'll be way faster. And a lot of times it proved to be true, even though it took quite a bit of trials and tribulation to get there. So in the example here where you're not streaming, imagine we're sending this like chunk of video over, and we're just doing one big chunk that we can play, and maybe even more than we can play at a time. It's slow. But if we break that up into smaller bits, and we know that we can start playing it before we get multiple frames of video, then we can send over these little chunks a lot faster. At some point, the overhead of sending these chunks is more than, it slows it down more than if we sent one big chunk. But the good thing is that we got enough chunks over fast enough to where we can start playing the video sooner, which improves utterance time. Okay? Which is okay. Because we're faster to that first meaningful chunk, which means that we're faster in terms of response. All right. And it's something like n times faster up to a certain limit. So the smaller the chunks up to a limit, the faster the utterance to utterance is. And we're trying to get that down to like one frame of video that we render and send. And it's pretty challenging. We're getting pretty close, though. Parallelism. The next thing, the tool that we applied was parallelism. And that's the idea that what if there are multiple things that we can do at the same time, let's do them. We're running this on a GPU in the cloud, and we have so many processors. Let's say we have 10 processor cores, and we have a NVIDIA A100 or something like that. And we have all this power available. Well, if it's just sitting there idle and there's something that we can do to get ahead, we should do it. And so this is kind of a rough look at the parts of a conversational replica or a conversational video interface on the back end. And these are some of the things that happen. So there's like capturing the audio stream. So you actually have to capture the audio stream, put it somewhere. Then detecting speech, detecting when someone stopped speaking, when someone started speaking, detecting or accumulating up that audio, transforming that audio into text that the LLM can understand. And then simultaneously, we need to be checking out the scene, asking questions about what's going on in the scene, and then sending that to the chatbot. And then the chatbot needs to send out its text, and then we have to figure out which chunk of text makes sense to say. And do we have to wait for a whole paragraph, or can we send, how much do we need to send? Then we have to convert that text to speech, and then convert the speech audio to video, and then send that back out over the network back to the chat room, or the meeting room. So all those things have to happen within under a second. And a lot of that happens in parallel, actually. A lot of it happens, you need what the user said to transcribe it into text, and then you need the text to feed to the LLM for it to decide what to say next. And so if you were to just do that serially, your throughput's pretty small, right? So you're just sending this one little chunk of data through, and that's okay. But the problem is that if you had to wait for all that to happen and you could just do that, then your utterance delay is the time that it takes for all those to run. So that's where parallelism comes in. And if you can run all of them simultaneously, and you probably all know this, and none of these are magic tricks, these are all really basically good engineering, then you can do it faster. And it's nx times more throughput. And more throughput means that you can, that throughput and latency are different, but throughput at some point limits your latency. If the amount of data you need to send is more than your throughput, then you're digging into your latency at that point. So we decided to go with a task-driven architecture where we have multiple different things running in parallel. That looks something like this. And it was way faster. Okay, the next thing that we ran into was that a lot of our stuff, a lot of our data that we use, our weights, our source material was stored in S3. And then, we could download it from S3, but then it's on a disk, right? And then we're trying to get ahead of everything, trying to increase our throughput so that we don't dig into our latency at all. And so the faster everything can go, the better. But we started seeing that like parts of our inference started hanging or going, or their bandwidth was a little too low, which started digging into our latency a little bit. And the more we dig into our latency there, the more we get behind in other places, and it kind of like, it just makes everything more complicated. It's better if we can just be faster. And so we started looking at moving all of that data as much as possible into memory. But depending on the model we were using, the memory, different amounts of memory were available. And so we had to kind of adapt as we went. Where we ended up at was that like the more we could put in memory, the faster it was. Very, very basic, very simple. And so here's kind of an illustration of what we figured out. Okay, so moving it into memory and then moving it to the process is really slow. But if you can actually put that source material in memory and keep it there, and instead of moving it, you just move the pointer to that, it's really fast. And so that little improvement shaved off like 1.5 seconds of utterance to utterance. So that's like CPU memory. Well, what if we took it further and we just kept things in GPU memory as much as possible? Like we have a multi-process system, but what if we could keep things in GPU memory? That would be great. And the reason that's great is that the further away you keep something from where you're using it, the further it has to travel and the longer it takes. And so if you can optimize things by moving your data closer to where you're processing it, you can act on that data faster and reduce your latency. And so we're just having things in GPU memory, and the processor over here is able to really quickly work through that data. And we ended up increasing our frames per second on our visual model by 4x there, bringing us up to like 95 frames per second, which allows us to get ahead. Because our video plays at a natural 25 frames per second. So now we're rendering the video almost 4 times as fast as we can play it. All right, so what's next? Well, customers that we've talked to so far, and Delphi is one of our customers, have asked for faster boot times. Now we have like several gigabytes of data that we have to make available on these machines, and we are trying to make this system scalable. We use a partner, GPU partner called Replicate for that, and in order to be able to make this scalable to say like 300 streams, we can't have all that data on all these machines because we don't want to pay for all these A100s all the time if they're not being used. So we essentially have to download that data onto the machines, which takes time. And so right now we've got our boot times down to around 10 or 15 seconds. And one of our goals is to reduce that down to about 5 seconds or make it instantaneous. So we're working on that right now. Faster utterance to utterance. Right now, our fastest utterance to utterance we've measured was 600 milliseconds. And I think that we have a way to get to 200 already. So we're working on that. Interruptibility, we already have that, but we can improve it. We can make it better, more responsive, more natural. Maybe some way of the bot not immediately stopping talking or something like that. And then more on the infrastructure side, things like events, observability, and an API. So we currently have an event-driven system where when the bot is doing things, like if it's speaking or listening, we send out an event to let people know. If when the bot joins the room, we send out an event. If there is any kind of issue, we let them know we let you know what's going on through an event. But we also have a REST API where you can interact with the system that way, and it's very simple, very easy to use. Okay, so these are the lessons on speed. So separate the steps thoughtfully. There was a point in time where we separated events too liberally, or separated processes too liberally, and that actually cost us in boot time. Even though it sped up our inference speed, but it wasn't really resulting in better overall utterance-to-utterance improvements. And so we had to actually kind of recombine some processes back together thoughtfully so that we don't have to spawn a new process, which takes time. Coordinating parallel processes carefully. When you do things in parallel, you need a way to like real-time coordinate between the different processes what's going on. Things like clearing the audio buffer when the replica is interrupted, or stopping the LLM from generating new tokens when the replica is interrupted, or deciding when to send frames that are silent versus when to send frames that are speaking. And then the last two things I talked about were moving smaller chunks and keeping things in memory as much as possible. And so ultimately, we were able to achieve anywhere from, like, our utterance to utterance right now is about 600 milliseconds to 1.3 seconds. And the great thing about that is it feels kind of real. Like, if you haven't tried it, give it a shot. It's on our website, tavus.io. It feels different. I think it does, even though I've been working on it for 3 months. And a lot of people have given us that feedback. I'd love to hear from you what you think. Do you think it feels different? Let me know. Hopefully it creates more of an authentic connection because you're talking to a person, you are seeing a person, and they're responding to you, and it's more ergonomic, more natural, more kind of what you would expect out of a conversation. And we try to make it easy. I think we do make it really easy with our API. It's a REST API and quite easy to use. Some of the use cases are things like e-commerce. My dream is to have Michael Jordan on the Nike site selling you Michael Jordan or Air Jordans. And so as you scroll through, he has some agentic capabilities on the back end, and he checks you out, and he's like, yeah, I think you're going to like these Air Jordans. Let me take you to the page. And he brings them up, and he's like talking to you. He can hear you. You show him what you're wearing, and he makes suggestions. Or like, what about like a sales representative? Like a lot of times with the early cold calling or just follow up, it'd be nice just to have something that can go and talk to people in your likeness, gather information, figure out where they're at. They feel less pressure because they're not talking to a real person, but it's still you, and it's your authorized representation of yourself. And then things like customer tech support, where the person, it just needs to feel like comfortable for someone, where they don't want to they want to see someone, feel like a natural connection, because it's already stressful enough. And like seeing a person and hearing a person and having an interaction with a person kind of makes us feel better. And then things like tutoring and coaching. And the product's already loved by our customers. And I think we really try to take a developer-first approach, and it's one of our key differentiators, that it's not just having a great replica, it's not just having a great conversational video interface or having a great API. It's the fact that we really want to listen to our customers as developers and move the needle for them. So we're not just trying to build the coolest thing, we're also trying to build the coolest thing that serves your needs and helps you build what you need to build. So that was my talk. Check us out here on this website if you want to try the demo. Feel free, and thank you very much. And I've got a little time for questions. So.
I noticed a small thing with the interjections, like haha, that definitely was like, it threw me a little bit for a loop. So do you have any plans to like effectively replace or maybe tune that specific piece more? Or that one was really kind of threw my brain off for a second, because the haha was very artificial in my mind.
Yeah, that's a good question. What he's asking about is right now, if the bot, I guess you heard it, laughs, instead of going ha 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 ha, ha, it goes ha 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 ha.
Projection.
Okay, because it's reading text. So yeah, we don't have immediate plans to do that, but we are looking at it, and it's something that we want to improve for sure. So that's coming up. Yeah.
Thanks so much. I noticed, like you had said, you do one frame at a time on the streaming, at least on the diagram, but at some point there's like a cost benefit of like maybe giving a little bit more data to get that first response so that it can be higher quality. So how did you think about that trade-off of like making, bigger chunks that could be higher quality versus like time to first response?
Yeah, it's definitely a balance. So what he's asking about, it's a good question, is when you send, so he's asking if we send fewer frames to make the utterance to utterance or the latency better, do we lose quality? And how do we balance that trade-off? And so our Phoenix model is kind of unique in that is designed to render a single frame at a time. It's using a context window to make that possible, but it's only it's capable of rendering a single frame at a time and have the same visual smoothness as rendering a batch. The issue is that when you start getting small, like I talked about, too small, the overhead of sending a frame becomes large enough to where you can't keep up anymore. And so we're really tuning as far as we can down to that single frame as possible, and we haven't gotten there yet. But we have a really strong bar on quality in terms of our vision, so we're really holding that line and trying to push as far on the engineering as possible to make that happen. And it really comes down to faster rendering. The faster we can render, the more we can keep up with that. There are a couple other tools in our tool belt too, but maybe I'll talk about that on the next talk. It's a more in-depth.
One more question. Anybody else? Oh.
Can you talk a little bit more about what you've learned about the pipeline for just focusing on the speech part, detecting that somebody's speaking and then what they're saying? But that's something that I've been really curious about is how do you, like there's obviously text to speech, but all the other components that go into that pipeline.
Yeah, so that's a good question. What he's asking about is what are all the components that go into not only figuring out what someone said, but figuring out like when they've stopped talking, right? When did they start talking? Like those things matter. And that was probably one of the more tricky parts of the pipeline because people stop and start talking a lot. You heard me just then, I took a pause, right? And so it's not only just about that part of the pipeline, although that has to be good. You've got to think about the rest of the pipeline. And how do you handle situations where you thought they stopped talking, you thought somebody was done, so you sent off some text to the LLM, and the LLM generated a response, and then it sent it to downstream, but then you start talking again. Did you have a back and forth with the replica, or are you still continuing your thought? And how do you deal with that? That's one aspect of it. The other aspect is around just the mechanics of dealing with noise is one of the tricky parts. Like noise in a noisy room like this, it's really tricky to, like if anybody was talking in the room and the microphone picked it up, then the auto speech recognition would start transcribing it. Well, things get really tricky when you do that. So we did some tricks around noise and trying to focus in on the user's voice. We've tried a lot of off-the-shelf stuff. We ended up kind of building our own thing that we feel like is better for now because it's very fast and it's also very good at figuring out when people stop talking and when they start talking. So I could maybe go into more detail about that later. All right, well, thank you, everyone. I appreciate you coming out, and thanks for the questions.
Thank you, Brian.